Hi, everyone. So we are officially on the last chapter of the semester. That'll be chapter 5. And we only have, I believe, 4 sections. We'll do 5.1, 2, 3, and then 5. We'll skip over 5.4. So we're in the home stretch. I hope it feels decent. We will have the final coming up soon, and you will have more information about that probably right around now. Again, these are pre-recorded. These will all have been recorded before the class even starts, so you will get information if you haven't already very soon. All right, so this is chapter 5, and this is chapter 5 on integration. So in the last lecture, 4.10, we discussed antiderivatives, and we said how taking the antiderivative of something was integrating it. And the symbol in front was the integral sign, and that the act of this was like the integration of some function. And so chapter 5 is all about integration. It's all about antiderivatives. So let's go ahead and start with 5.1, approximating areas. So like I mentioned, derivatives and antiderivatives both have a lot of applications, especially in the real world, as opposed to some other math courses you may have taken. Um, so for derivatives, we've discussed how they relate to, say, velocity and acceleration. Also, if you've taken physics or will be taking physics, especially calc-based physics, you'll see a lot of derivatives and stuff like that in physics. They have so many applications. Um, Antiderivatives also have a lot of applications. So in fact, if you take Calc 2, you'll see more than what we're going to cover here. So what we're going to cover here is how antiderivatives can actually give you area under a curve. And by curve, it's a very broad term. So that could be a straight line, that could be an actual curve. Curve just means some function. So we're going to be looking at how integrating something is actually taking the area under the curve, finding the area under the curve. And you also can find volume of a three-dimensional shape using integration as well. So there's actually some really cool applications for the real world that come into play when you look at calculus. We won't be doing the volume in this course. All right, so the first couple of slides is really going to be establishing notation. So you don't need to write all of this down, just kind of get down the notational parts and understand what I'm kind of talking about. So we are going to be using this notation at least for today. And this is something, again, if you go into Calc 2, you're going to see this notation. And I imagine if you take other courses, you either have or will see this summation notation. You've probably already seen this in like a high school math course when you were talking about sequences and series. You probably saw some kind of summation notation there. Now, whether or not you remember it, that's another story. That could have been a very long time ago. But regardless, so this is something called either sigma notation or summation notation. Both are used synonymously. And it's written like this. Um, it looks like this, and it's read as the sum from I equals 1 to n of a sub I. All right, so you're going to start with the ith term, and you're going to plug in 1, 2, 3, 4, all the way up to whatever value n is, if you know what n is. So for example, if you have the sum from I equals 2 to 7 of s sub I, we may not know what s sub I is. It may be some function with some values, but we don't know them. So the sum is simply plugging in from 2 to 7 into your I. So that'll be um, plugging in 2, but then the sum indicates that you're adding all of these things. So that's why we have a summation notation. So that's going to be s sub 2, but plus the next one, s sub 3, plus s sub 4, plus s sub 5, all the way up to 7. So this is what it means to be a summation notation. As you see, I is called the index right here. This is the index. And then this will just be, this is also an index, but it's just the highest term that you'll go to. All right. This is just another example of summation notation. I'm not going to ask you to reproduce this. You will, if you take Calc 2, look at a lot of summation notation when you're looking at sequences and series and determining a lot of things about sequences and series. You'll have to kind of determine patterns and use a lot of pattern recognition in that. But here, this is again just for your understanding. So I'm not going to do A. I'm just going to take a look at B, write the sum in sigma notation. So what we see here, this is going to be a Calc 2 topic later on down the line. But again, for your understanding, what we see here is we have a sum of 5 terms, and you notice that the numerators are all going to be 1. And in fact, I'm going to rewrite this 1 as 1 over 1. And you notice that the denominators are increasing. And in fact, what you should recognize is that each one of these is a perfect square. So for example, 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 4 squared, 5 squared. So if we're looking to write this in sigma notation, we would write the sum from I equals, usually we'll start at 1, sometimes we start at 0, to, well, we have 5 terms, so we'll go to 5. And then we have to create the function that we're looking at. Well, we see the numerators are constant, so we're going to put 1 over because nothing is changing here. But what is changing is our denominator. So what you notice is the first term starts with 1 squared. But then when you plug in the second term, that's 2 squared. So the second term, you plug in a 2, which is exactly what we have here, 2 squared. For the third term, you plug in a 3 for I, which is exactly what we have here, 3 squared. So what this tells me is if we had something like 1 over I squared, this would give me exactly this, because it would be 1 over 1 squared plus 1 over 2 squared plus so on, and that would give me exactly this. So this is just the idea behind sigma notation. All right, and these are some properties behind it as well. So if you have the sum from I equals 1 to n of some constant, this is again not something that you need to memorize for this class necessarily, but if it is something that you're going to be maybe taking the Calc 2 course in the future, this is something to maybe just keep in the back of your mind. If this isn't something that you're going to be doing, if you're not going to be taking a Calc 2 course or any other courses in math, and you're just kind of taking this as like a prereq for maybe physics or something like that, you can kind of more or less ignore this slide. So if you sum a bunch of constants, you actually just get whatever the highest index is times the constant, which would make sense. You're not actually plugging any numbers in, you're just adding c I or n times, which is n times c. That's just multiplication. We have the same idea as like derivatives and antiderivatives, that if you have some constant attached to whatever your sequence is, you can just pull the constant out and it doesn't affect anything. So that's what this is saying. We also have a rule similar to, like I said, derivatives and antiderivatives, that if you have the sum, and in fact, we are going to relate this to an antiderivative. Sums and antiderivatives are very, very closely linked, and I can kind of explain that a little bit further. But essentially, an antiderivative is going to be like an infinite sum. So the sum plus or minus is just breaking it up into the sum using the same indices and keeping the sign in between them. So you can sum up individual terms. And then we also have this last rule that says that you can have maybe a sum from I equals 1 to n, but maybe you want to break it up slightly differently. Maybe you have values that make a little bit more sense to use. So say you want to stop at m, you can do that. You can say I to m, where m is less than n, as it says here. But then you also have to consider that there are more values. So you're going to pick up at m plus 1 because that's exactly the next term in the sequence. And you have to finish off at n. So you can split it up however you'd like, if it makes more sense to do it like that. All right. There are also a few sums that are just kind of good to have on hand, good to know. Again, if you're taking Calc 2, if not, ignore this, you can skip ahead. But if you're taking Calc 2, these are some sums that are just kind of common knowledge. So you may see this in a problem and you're expected just to kind of be able to reproduce exactly what it is without needing to like do any computations. So for example, the sum from I equals 1 to n of just I is going to be n times n plus 1 over 2. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. I don't necessarily think that we see I cubed quite as much. So if you're going to memorize 2, it would be these two. But I cubed probably isn't a bad one just to kind of have in the back of your head. These two, especially this one right here, the first one, the sum from I equals 1 to n of I being n times n plus 1 over 2, this one comes up quite a bit in terms of like solving stuff. All right, now we can actually talk about what this means in relations to like area. So how do we approximate the area under a curve? Given that we don't yet have a definition in terms of integration and what it means by area, as I've kind of alluded to the fact that like this is how we would compute this, we actually have a different method that we want to do this to start. So what we want to do is we want to use something called left endpoint approximation and right endpoint approximation. So say we have this random curve f of x, we want to approximate the area. We can approximate it using left endpoints and right endpoints. So what does that mean? Well, first we have to consider the idea of what it means to be a partition. I assume that most of you have heard this word in some capacity before. This is going to be the mathematical definition with notation. Again, you don't have to memorize this specific notation. What you need to know is the idea of a partition. Specifically, you're going to need to know the idea of a regular partition. So we don't use partitions that aren't regular. What I mean is you're not going to have like the interval from 1 to 4 and then like 5 to 25 and then like 25 to 6 to 26. Like that just would make no sense for us. So you're going to have it in regular intervals. So maybe 1 to 2, 2 to 3, 3 to 4, or 1 to 3, 3 to 5, 5 to 7, where they're all going to be the same width. So a partition is just kind of where you break up, say, A to B into different intervals, where A is going to be equal to your first term, and the first term is obviously less than the second term, which is less than, and you can continue going on like this, and then the last term is going to be equal to your B value. And you can break it up into intervals that kind of look like this. We will be dealing with regular partitions for this lecture of A to B, which means that the intervals that we're going to be looking at are going to be equal. So as it says here, if the subintervals all have the same width, then it's a regular partition. That's what we care about here. All right, so just keep that in mind. All right, now we can discuss how to find the width of those partitions. So there's a lot of writing on this screen. Again, I'm going to highlight the part that you should know. So given some A to B, sometimes we want to divide it into n subintervals. A lot of times they'll give you the actual number. They'll say divide it into 4, divide it into 6 subintervals. They'll give you how many subintervals you want to divide it by. So that's when you plug that number in. Given some interval A to B with n subintervals, the width of your intervals are the equation b minus a over n. So it's exactly this equation right here. So this is how you'll determine the width every single time. You can also denote it as the change in x. So you'll see this quite frequently in the definitions that we're going to be looking at. So it's going to say the change in x, and that's just b minus a over n. All right. Maybe we don't have to worry about the rest of what's on the slide right now, because honestly, this is going to be the most important part. And I'm going to try to simplify things as much as possible for you. All right. So just remember that the change in x, the width of your subintervals are b minus a over n. All right, so now we can start talking about what it means to find a left endpoint and a right endpoint approximation. So first, let's consider left. So given n subintervals, in order to use a left endpoint approximation, we are going to construct rectangles, because what we're looking to do for area, for approximating area, is we're looking to use shapes that we know to find the area of, to approximate those rectangles. So if we look here, if we're looking to approximate the area under this curve here using left endpoints, we want to make a rectangle because we very, very well know how to find the area of a rectangle. We know the area is length times width. And so if you're using left endpoints, well, the left endpoint would say, okay, go up to the y value. And if you know the width of that rectangle, the width of each rectangle is going to be the same, because that's all we care about, is going to be regular partitions. And so to determine the rectangle, well, you need to go over by the width and then drop down again. And so the area of this rectangle is going to be the width of your rectangle times the height of that rectangle, which is just going to be your f value. So if this is f of x, then your area is going to be x times f of x for whatever x value you have. And you're going to do the same thing for every point that you have. So for the next one, you're going to go straight up until you hit your curve that you have, and then you're going to go across however far your width would go and drop it back down. Here's another rectangle. And so what this is actually going to look like is your area is going to be whatever your width is. So that'll be your b minus a over n. And then what you're going to do is you're going to sum, as it says right here, you are going to sum up all of the f values. So it's going to be the change in x. I'll use that notation instead, because we will have computed that, and that's going to be a constant value. So you're going to have the change in x times, and then what you can do instead of writing it out like this, as you see, there's a change in x in every single one. We'll factor that out to make it a bit easier. So you'll have f at your first point. Oops, no parenthesis after that. And then you're just going to kind of add up all of your y values. Plus f at your second point, plus, and then f up to x n minus 1. And the reason why we go to n minus 1 is because, as you see, here we have 4 rectangles, right? So we hit here, and then for the last one, we go up, left, and down. But what you don't see is for this left endpoint, you don't see, let me use a different color. Move my face. What you don't see is this point right here being used, because if you were to use this point, you'd have to draw it up, go over, and down, but you'd be using a 5th rectangle. But that's not going to be within the range that you're looking at. And so if you're looking for left endpoints, you're going to be omitting the very last term. If you're looking for right endpoints, you'll omit the very first term. I'll show you an example of exactly how we'll set that up in a minute, but this is going to be the construction of that. This is also the definition of the right, and we'll call it like R sub n. The other one we can call L sub n, or you can just say like area sub left if you'd like. And it's the same exact thing with right endpoints now. As you see, we're not using the leftmost endpoint. So because there's going to be 4 rectangles in this case, there's going to be 5 x-intercepts, which would make sense. So we just want to use the 4 rightmost endpoints, because if we use this one, we would be constructing another rectangle, which would exceed the number of rectangles that we want. And so this right here is the idea that we're going to want to use. So we're going to want to have the change in x, and then we're going to want to use the first one, omit x sub 0, omit the very, very first x-intercept y value. And we're going to start at the second and go until we hit the last one. So add this until we get x, f of x sub n. And this is going to be your area formula for right endpoint approximation. All right, so here's an example. Use both left endpoint and right endpoint approximations to approximate the area under the curve f of x equals x squared on the interval 0 to 2. Use n equals 4. This is typically the type of information that you would be given. You're going to be given an n, an interval, and a function. You may not be given a graph, though. If you're not given a graph, I do suggest drawing the graph, because sometimes it just makes it a little bit easier to actually sketch in the rectangles to see, like, oh, well, I've used this many rectangles, which means that I cannot use any more, so I can't use this last endpoint. So for left endpoint approximation, let's first sketch in the rectangles. You can see 3 rectangles, but what you don't see is the 4th one. And the reason why you don't see the 4th one is because you start at 0, right? So if we have 0 to 2, then the change in x, and this will be the same for both the right and the left because the intervals don't change. The change in x is b minus a over n, right? So this is a and b, so that means that we have 2 minus 0 over, and n is 4, which gives us 2 over 4, which is 1/2. So each rectangle has a width of a half. As you can see, this is divided into a half. Using left endpoint approximation, we want to start at 0, which is the very first value in our a to b. Right endpoint will start at 2 and go the other way. So we'll look at left endpoint first. We're going to start at 0, but that's on 0. So if you're trying to consider a rectangle, well, you can't go up, right? Because that curve hits at 0. So you can't move up, which means you could only move to the right. So in fact, it's not a rectangle, it's just a line. And if you try to compute the area of a line, you're not going to get anything because you get 0. Because the length times the width, well, the length or the height of this thing is just 0. So 0 times anything is 0. That's why you don't see a 4th rectangle here. So for 0.5, you draw it, go up to the function, and then you go over however far your width is, drop it down, and then you go up, over, down. So we've created 3, up, over, down. We've now created 4. As you see, the points that we're going to be using for the left endpoint approximation are going to be here at 0, here at 0.5, 1, and 1.5. You notice we omit the 2, because if we were to use the 2, we'd be creating a 5th rectangle, which violates the number of rectangles they want us to use. So what I'm going to do is, typically you will be asked for left and right endpoints. You'll be using the same function, the same interval, and the same number of rectangles. So I'm going to write down all of the values right off the bat. So I'm going to say f at 0 equals f at 1/2 equals f at 1 equals f at 1.5 equals, and f at 2 equals. Because from there, it makes it a lot easier to do our computation. So f at 0, plug in 0, you get 0. 1/2 squared is going to be 1/4. 1 squared is going to be 1. And again, I'm just plugging this into the function that we're given, whatever that function may be. In this case, it's x squared. 1.5 squared is the same thing as 3 over 2. So 3 over 2 squared is 9 over 4. And 2 squared is just going to be 4. So I suggest writing down all of the values, all of the possible values, not just for left or for right, but all of them right off the bat. It will make it 10 times easier once you're actually doing the computations. Because now you can do the area of the left, or you can also say, what was the notation that we used here? R sub n. So you could say A sub L, or you could say L sub 4. So this says that we're left endpoints with 4 rectangles. Either way is absolutely fine. I don't really care how you denote this as long as you like specify what we're looking at. If you just say A for both of them, I can't tell if you're talking about the left endpoint or the right endpoint approximation. So make sure you specify what you're looking at. However you want to do that is up to you. If you want to say A equals, and then at the very end, write this is the left endpoint approximation, that is okay too, but usually it's a little bit better to denote exactly what you're looking at from the beginning. So in order to find the left endpoint approximation, we need to add up all of the rectangles. Again, since we know the change in x is constant, this is going to be the change in x times the sum of these x values. So this is, I will just write them from the start. So the change in x we said was 1/2 times, well, the first one is f at 0 plus f at 1/2 plus f at 1 plus f at 1.5, not 1 over 2. We have that one already. 1.5. And you notice that's all of the rectangles we have. If we did f at 2, again, we would then have 5 rectangles, and that would be an issue. So what you always want to do is you want to make sure that the number of f values you have here matches the number of rectangles. If you have too many or too little, you need to go back and find where you're missing or where you have too many. So for left, you want to start with the lower value, and then you're omitting the top one. Again, for right, you want to start with the top one, and you're omitting the lower one. And this is why I say write them down from the beginning, because then you're not computing them in here. So now this is 1/2 times, and then you just add them. So 0 plus 1/4 plus 1 plus 9/4 plus 4. And we can go ahead and compute this value. So let's see here. This will be 4 plus 1 is 5. So this is 1/2. So I'll adjust the 5 to have a denominator of 4. So that's 20 over 4. So it's 20 over 4 plus 1 over 4 plus 9 over 4, which is 1/2 times 20 plus 1 is 21 plus 9 is 30. So this is 30 over 4. And I multiply across, I get 30 over 8. And I may want to simplify this to be maybe the simplest fraction, but it's not necessary. So this is the value for the left endpoint approximation, 30 over 8. And again, since we're not allowed to use a calculator in this course, if you have a fraction for this value, and this is like an exam, I'd probably be like, that's a little bit weird. Question mark. If the number was like a 2 or a 4, I'd trust that you probably know how to do that. An 8, unless you've really memorized those values, I might be a little bit more skeptical of. All right, now let's look at the right endpoint approximation. I'll use a different color for this so that it doesn't get confused with what we have here. All right, so for right endpoint approximation, we're going to start on the right-hand side. So we're going to go to 2, because that is the furthest right. We are going to draw up until we hit the y value, and then we're going to go across for however far the width is, and we're going to drop back down to the x-axis. And we're going to continue to do that until we have 4 rectangles. So we go across and down, across and down, across and down, using the points on the curve. So that's this point here, this point here, this point here, and this point here. What you notice is we're not using 0. So that tells me that, say, the right area with 4 rectangles is going to be the change in x, which is 1/2, because that's the width of these rectangles, all of them, times, well, now we can start from the right. So this is going to be f of 2 plus f of 1.5 plus f of 1 plus f of 1/2. And again, you notice we have 4 here. We're omitting the 0, because if we use the 0, that'd give us 5 rectangles. So this is 1/2 times, And again, that's why this becomes so much easier. So this is 4 plus 9 over 4 plus 1 over 4, which is, let's see, so this is again 5, so this is 1/2 times 20 over 4 plus these I can combine to be 10 over 4. So that's 30 over 4 times 1 over 2 is going to be 30 over 8. Okay. I've done something. Oh, you know what? So what I've done, so this is going to be my learning experience for you. What I've recognized is that somehow I computed the same exact value for the left and the right, and that is never going to be the case. This is not an exact computation. You should never get the same value. Because what you see is this is going to be an over approximation, right? So this is above your curve. These are going to be an under approximation of area. This is below your curve. So what you notice here is maybe you caught it when I was doing it and you were like, no, stop, stop. You're doing it wrong. You just said that there should be 4. Anyway, I added all 5 values. That is wrong. I don't want that value. So let's go ahead and fix that. So again, this is how I can identify that I was doing something incorrect. So I'm going to erase all of this. So I don't want to add that 4 in. This should be the under approximation. So what I actually get, and I'll change this back to red, is 1 over 4 plus 1 plus 9 over 4. So if I change this to 4 over 4, I get 9 plus 4 plus 1, which is going to be 10, 14. So 14 over 4, which is going to be 14 over 8. So this will be the area on the left, which as you can see, this is definitely an under approximation, and this will definitely be the over approximation, and they are not the same number. So sorry for doing it wrong, but honestly, this was probably a good like learning experience to see that like even I can make a mistake, and this is how you identify how to fix the mistake and that there was a mistake in the first place. All right, here's an example of f of x equals x minus 1 cubed plus 4. This is already drawn out because absolutely no way in you know what would I ask you to draw out 32 rectangles. That would be awful. But as you can see, the more rectangles you create, the more accurate your approximation is going to be. So from here, this last one, you see there's a large gap here and here. In fact, this goes over, like way, way over here and here. So this is like a way over and a way under approximation, which isn't super great when we're actually trying to approximate it. Like we really want to know the number. So the more rectangles that we use, the more accurate our approximation is going to be. So here we have 32, and we notice that it only goes over a little bit here. This is almost exact in the middle, and it only goes over a little bit here. So you see in this table right here, again, maybe you don't have to write anything down. This is just kind of for your understanding. If you have 4 rectangles, then your left area approximation is going to be 7.5, and your right area approximation is going to be 8.5. So you see this will be a little bit of an under approximation, and this will be a little bit of an over approximation. If you use 8, now it's a little bit more accurate. You notice these two numbers become a little bit closer. Now, if you use 32, this number is almost 8, and this number is almost 8. So in fact, if you took n to be infinity, what you would get is that L sub n equals 8, which equals R sub n. So if you were to actually use the technique that we'll be doing in the next lecture, which is going to be using like a definite integral, what we'll be able to determine is that the answer will in fact be 8, like a solid 8. So the more intervals or rectangles that you have, the more accurate your area is going to be, which seems to make sense. All right. So now we get more of like the formal definition. So we've been kind of referring to it as left endpoint and right endpoint approximation, and that is what it is. But it's more so something called a Riemann sum. So if you take Calc 2, you will be kind of starting off with this idea of Riemann sum. This is presented more in the beginning of the course. And a Riemann sum is essentially just like using the left endpoint and the right endpoint approximation to approximate the area. So F is defined on A to B. You have a regular partition of A to B. The change in X is the same as we had, B minus A over N. A Riemann sum is this right here, where X star is any point in this value. Typically, we will use like the lower Riemann sum and the upper Riemann sum. So maybe you don't have to necessarily memorize this notation, just recognize that it looks almost identical to the left and the right endpoint approximation. So with Riemann sum, usually you'd be asked for like a underestimate and an overestimate of the Riemann sum, in which case you would just be looking for lower and upper um, kind of uh, approximation of area. Depending on the curve, it may not be that the lower approximation is the left endpoints. So you'll just have to be careful about what curve you're given. All right, now we can kind of introduce the notation of, or the idea of area under the curve. So this is a very large concept. So if f is continuous and we have this Riemann sum, then the area under the curve is in fact the limit as n approaches infinity, which is what I mentioned when we were looking at the increasing number of rectangles idea. The limit as n approaches infinity of your Riemann sum. So once you get infinitely many rectangles, which obviously isn't possible because infinity isn't a number, but if you were to use infinitely many rectangles, you would get an exact area. And that area would be the area under the curve. So this is the idea behind area under a curve. And like I said, we will show in tomorrow's lecture how that relates to an antiderivative. And in fact, that's so much easier than using this, but this is the idea behind it. All right, this will be the last slide for today. This is going to be the application of exactly what we've been doing. So this is find a lower sum. I'm going to add to this. I don't just want a lower sum, I want both. So find a lower and upper sum for f of x equals 10 minus x squared on 1 to 2 with n equals 4 subintervals. Okay, so we're going to approach this the same way that we approached the other one. The first thing that we have to do is we have to find the change in x. We need to find the width of our subinterval. That's probably the easiest thing to do. The change in x is b minus a over n. So here's b, here's a, so that's 2 minus 1 over n, which is 4, which tells me that this is 1 over 4, which is also 0.25 if you'd rather graph using decimals. All right, so this is 0.25. Now, we know that we need to increase in increments of 0.25 from 1 to 2, and we need 4 subintervals. So what we're going to do is we're going to find those values now. So I'm going to say, well, we need to start at 1, so f at 1, and we're going to plug that in here. So 10 minus 1 squared is just 10 minus 1, which is 9. Now, I know I'm increasing by 0.25, so I need 1.25. And instead of, making you sit through my calculations, I just kind of have them sit like written right here. So this is 8.4375. And like I said, it's very important to kind of get them down from the beginning so that there's a little bit less room for error once you get to the actual computations. F of 1.5, because we've added another 0.25, is going to be 7.75. Oops, 7.75. If you were asked to find anything like this on an exam or anything, you would be given values that you can compute without using a calculator, because again, you're not allowed to use a calculator. So you would be given values that maybe don't look like this. F of 1.75 equals 6.9375. And then f at 2, and we see we stop at 2 because that's the upper bound on this interval, is just 10 minus 2 squared, which is 10 minus 4, which gives us 6. All right, so now that we have all of these, if we wanted to graph, we could actually see exactly what this curve is going to look like. So if we did like 1, 2, and we divided this up, 0.25, 0.5, 1.75, we could theoretically graph this if I had like, here's 5, here's 10, so here's 7.5. We could graph this and say, well, 1 is at like 9, 1.25 is at like 8 something, 1.5 is like 7.75-ish, 1.75 is at about 6 point something. My graph is not looking too accurate. Let me just redo this. It should be a little bit more of a gentle curve. So it should be like this, like this, like this, like this, and then like this. And when you connect them, it's just kind of like a gentle curve going down like this. So that's a curve that we're trying to approximate the area of. All right, we want to find the lower and the upper sums. So what we want to do first is now looking at this curve, kind of determine which one the lower and which one the upper is going to be. So if you look at the lower and you draw an arrow or a line going up, I'll use red, start here, go up, go to the right and down, and then again, kind of here, right and down. You notice that these are all occurring above our curve. So the left here is actually going to be the overestimate, the upper sum. So I'll say the L sub 4 equals, and then I'll denote this as upper. I'll just write it up here, parentheses upper, is going to be the change in x times our f of x. So I, and it's going to be the sum from I equals, we're going to start at 0 and we're going to go to I equals 0 to probably 3 here, technically. We don't need this notation, though. We can actually just write it down. I assume most of you probably won't be using notation, which you don't have to. So first we need the change in x, which is 1 over 4. And then we are going to add starting from the left. So that's going to be f of 1 plus f of 1.25 plus f of 1.5 plus, and then this last one is at, this should be leaning over a bit more. This was a very bad sketch on my part. F of 1.75. And we should, in fact, have 4 rectangles because we're using 4 here. And so what this gives us, I will just kind of give you the area is going to be 8.03125 if you were to compute this value. So this is when you plug in 1/4 times 9 plus 8.4375 plus 7.75 plus 6.9375. And this is the number that you get right here. Now, if you want the lower, this is now the right 4 rectangles. So this is again 1/4 because that's the width. But now we're going to start on the right. So we're starting with 2 because that's the rightmost value. And then we're going down by 0.25. And so we go 4 rectangles down. So that's f of 1.75 plus f of 1.5 plus f of 1.25. And again, with both of these, you notice for the lower or the left, we're omitting the upper, which is the 2. And for the right, we're omitting the lower, which is going to be over here. It's going to be the 1. So this is 1/4 times 6 plus 6.9375 plus 7.75 plus 8.4375, which again, I'll just kind of give you is 7.28. All right, so this is how you find your upper and your lower sums. And again, we know if it's upper or lower. Obviously, if we just compute it, we can tell, but also by actually sketching in the rectangles, we would be able to see if it's above the curve or below the curve. And that's how we know if it's upper or lower. All right, so that's all I have for Riemann sums and upper and lower estimates of area for today. If you have any other questions, definitely let me know. We will go into a little bit more about how to find area using what's called a definite integral in the next lecture. I think that will be a little bit easier to understand than what we're doing today. We'll be using some more regular shapes, some shapes that we probably understand the area of, and it's a little bit less kind of all over the place. So if you have any questions, as always, let me know. And if not, I will see you for the next lecture.